Hello, my name is Sandro Kofler and I am a PhD student with the Institute of Mechanics and Mechatronics at the TU Wien. Today I'm going to give you a short introduction about our project FC Impact. First of all, let's take a look at some key facts of the project. As you can see here at the long title of the project aims at increasing the market penetration of fuel cell cars by efficient system solutions. It is a joint project between the partners AVI List from Styria, IAESTA and ourselves, the Institute of Mechanics and Mechatronics at the TU Wien. The project is scheduled from October 2020 until September 2023, and it is a project within the FFG Zero Emission Mobility Program. A key advantage of the project is that there is a demonstrator vehicle available. This vehicle, which you can see here, was developed within the predecessor project, which name was KeyTech 4 EV. And by means of this demonstrator vehicle, we can finally test all developed concepts in the field. The decarbonization of individual transports is an ongoing topic, with several major car manufacturers already announcing their exit from fossil fuels. At the moment, there is mainly the battery electric vehicle in focus. However, also the fuel cell is a very promising candidate for powering vehicles because of some important advantages such as fast refueling, high energy density, and also the long driving range. This makes the fuel cell especially appropriate for heavy-duty vehicles such as buses or trucks, and also for vehicles that are used to cover rather long distances under a rather continuous power demand, such as vehicles that frequently are used to go on highways. However, when we take a look on the streets, there are still only a few cell vehicles out there. And the reason for that are several challenges that the fuel cell still faces, such as, for example, the high acquisition and operating costs, unexploited efficiency potential, and also the limited lifetime, which is prone to harmful operating conditions. At FC Impact, we directly address these problems in order to overcome these challenges. This can be seen in the main objectives of the project, which is increasing the overall efficiency of the fuel cell, increasing the lifetime, and also decreasing the costs of the fuel cell system. In terms of efficiency, we see here a typical efficiency curve of a fuel cell as a function of the output power. And we see here that there is a region where the fuel cell operates with a maximum efficiency. Naturally, when we are talking about increasing the overall energy efficiency of the system, we are aiming at operating the fuel cell mainly in this region here. And for this reason, we are currently developing sophisticated operating strategies. A particular objective here is to reach or achieve a fuel consumption of 0.8 kilograms hydrogen per 100 kilometers of under real driving conditions. The lifetime, as I already mentioned, is prone to harmful operating conditions, which include also a highly dynamic operation of the fuel cell. Here we are also developing control methods in order to avoid these harmful operating conditions on the one hand side, and on the other hand side, we are using information from real-time diagnostic systems that estimate some relevant fuel cell states and then communicate with the control systems. Last but not least, there are the fuel cell costs, and by developing virtual sensors, which are of course then applied to the final vehicle, far less expensive compared to physical sensors, we want to decrease the cost of the overall fuel cell system. There are also further secondary objectives such as improving the cold start behavior, including improving the freeze start behavior of the fuel cell, and also the general operation of the fuel cell under cold conditions. All in all elements that I have mentioned so far will then be integrated into the demonstrator vehicle and will be finally tested throughout a period of 6 months. We at the TU Wien mainly focus on the first 2 points, namely increasing the efficiency and increasing the lifetime of the fuel cell by developing sophisticated control methods. When we are talking about fuel cell vehicles, it is important to mention that fuel cell vehicles are generally conceived as hybrid cars. This means that not only there is the fuel cell stack as a power source, but also a battery. And the battery is mainly used for covering highly dynamic power requirements and also for energy recuperation. But as you can see, the overall system is a very complex one. And in order to control this complex system, we divide the system into different system levels, as you can see here. So we have here a top-level controller, which is basically responsible for determining an optimal power split between the battery and the fuel cell, and can also, if they're provided that if there is a forecasting system available, incorporate some predictive information. This can be, for example, elevation data or also environmental data based on the current GPS position and also based on the planned route. Then secondly, we have here the low-level controller, which is the controller of the fuel cell itself, which is a quite complicated system, including quite a lot of states. And here with the low-level controller, we aim at operating the fuel cell as efficient as possible. And thirdly, the third element we can see here is the diagnostic system that communicates with the two other control levels, and based on the information it gets from the other control levels, it estimates some important and relevant fuel cell states, such as the state of function, state of health, or state of charge, and then it transmits that information back to the control system, and based on that information we can try to mitigate the degradation of the fuel cell. Here I want to mention that those elements we can see here have already been investigated in other projects. And at FC Impact we particularly aim in putting these elements together in order to achieve a highly efficient operating strategy for the entire system. Let's take a closer look at the two control levels I already mentioned, namely the top-level control and the low-level control. The top-level control is the control at the system level and is responsible for the energy management of the system. Let's take a closer look at what this means. When we are driving with the vehicle at a certain speed and at a certain elevation, and also considering the driver information, this causes a certain electrical load for the system. And the task of the top-level controller or the energy management system is to divide and split this electrical power over our two energy resources, namely the fuel cell and the battery, by determining set points for both of them. And the objective here at this level is, of course, an overall efficient operation. This means we are interested in reducing the fuel consumption, mitigate degradation, and also to avoid constraints violations at the lower levels. Here, as I already said, we can also incorporate some predictive information if it's available. The method we are using here is a cooperative optimal control. The low-level controller is, on the other hand side, responsible for the control of the fuel cell. And the main objective here is, of course, providing the required fuel cell power determined by the energy management system of the top-level controller. Besides that, we also want to consider information of the diagnostic system, which is important in order to mitigate degradation, and also robustness against parametric uncertainties is important here. The method we apply here is a multivariate model predictive controller based on a sophisticated fuel cell model. I hope this presentation could give you an overview about our project FC Impact. Here you can see our project team consisting of Professor Jakubek, Professor Hametna, my colleague Zhangpeng Du, and myself, Sandro Kofler. And if you're interested in any further information, don't hesitate to contact us. Thank you very much.